Okay, so let me just conclude this review of some notations from differential geometry that we were doing last time, because we will need them for the proof. So if you recall, we had a manifold M, we had a manifold N, we had a point X in M, and then the tangent space those were the notations for the tangent space of M at X. And let me now assume that M is a matrix Lie group. So that so matrix Lie group, I will not write down in word, on the board what this means. I think you all know what a Lie group is. If you don't, it's very easy. A Lie group, it's a manifold, it's a smooth manifold like this one, which is a group. Okay, so the points on the manifold form a group, and the group operations, in other words, multiplication and inversion, have to be smooth maps. So that's it. And a matrix Lie group means that this is a group of matrices. That's the many Lie groups are matrix Lie groups, and we are interested in particular in the group of orthogonal matrices. So it has an identity, which I call I. It's a distinguished point on your manifold. It's the identity of the group, and the tangent space of the tangent space at the identity is called the Lie algebra. It's a linear space. It's the Lie algebra associated with the Lie group M. So let's just try to understand, to conclude this discussion, how to represent the tangent map on Lie groups. There's a particularly simple way of doing that. So let me start with recalling the exponential map. So let me take a vector in the Lie algebra. So this is something I will not prove. This is something that you will probably have seen in differential geometry. It's valid for any manifold. You can define the exponential map for any manifold. In particular, for matrix Lie groups, it's particularly nice because it's the actual exponential of matrices. You can define it as a power series. So this is this thing is in the Lie group for all t. So this exponential map lies in the Lie group for all t, and this is a convenient path. So this satisfies. If you recall, to define tangent vectors and the tangent map, one chooses such paths, and this is a convenient sort of a canonical choice of a path passing through the identity and pointing in the direction of x. So this satisfies, obviously, gamma of 0 is equal to the identity. That's the exponential. And gamma prime, or gamma dot, at 0 is equal to x. Okay, so we can make this choice of gamma. It's a particularly convenient choice. And now what we can do is we can transport. So let's try to draw. Maybe I'll try to draw this. So this is my Lie group. Here is the identity, and here is the Lie algebra. And let's say I have another point, little x, which has its own tangent space. And I would like to transport these notions over here. And what I can do is I can just multiply, since I have now a group action, I can take this path is somewhere here, and I can multiply this path, let's say from the right, by x. And I will get a new path, which is this path translated to the point x. So I can transport to X in the manifold. So then I get a new path, which I also call gamma. And so this is equal to e to the tx times little x. And this is still a point in M. M is a group. This is an element of M. This is an element of M. So this is all in the manifold. And now let's check. So gamma of 0 now is equal to x. And gamma dot, which is going to be my tangent vector. So this vector here is x, and this vector is a vector that I would like to call t. And what is gamma dot at 0? It's just big X times little x, and this is a tangent vector that I call t. So in other words, another way of writing this path here is that gamma of t. So given a tangent vector t here, I can find a canonical path, which is the following. I can solve t from this equation by taking the right inverse of x, or inverting from the right with x, and I get t. So here is my path. X is capital T times little x minus 1. And that's my. So these are all small x's. No, there's no big X left. Okay, so that's my path. And so the path defined using the exponential map, and now I can write the tangent map, and d. So this was the notation for the tangent map, if you recall, and this was just the derivative at 0, and you apply your function s to your path gamma. So this is going to be e to the t capital T x minus 1 times x. Okay, so this is a relatively explicit formula for my tangent map. Okay, yes?
There is two different x.
Yes, there is a big X and there's a small x. I try to distinguish them. Maybe if it's unclear. So the big X, the small x lies in the Lie group and the big X lies in the Lie algebra. So this big X, if I can try to add these serifs to the big X to make the distinction clearer. I think I caught them all, probably. Here's one more. This should be a big X. So this vector here is a big X. I think that's about it. Okay. All right. So this is what I wanted to say about Lie groups. So this was a very quick summary also to establish notations about Lie groups. But in particular, this is a convenient representation of the tangent map of a function between Lie groups. All right, is this okay? So let me now return to our problem of computing the Jacobian of this. So I will not do a full review of what we were doing, but let me just recall. So we had the map S, which was a map from the orthogonal. Let me so this is a map from the orthogonal matrices to times the diagonal matrices. Let's say the diagonal matrices with ordered entries, and it maps a pair, so an orthogonal matrix U and a diagonal matrix lambda. It maps it onto a Hermitian matrix, which is U lambda U star. So this is just a diagonalization map. And we saw last time, if you restrict these domains a bit, so if you restrict this to the matrices with distinct eigenvalues, and if you take the quotient here by the diagonal orthogonal matrices, then this is a bijective map. We had this integral formula where we computed the integral. So the goal was to find this integral, so the space over Hermitian matrices. And we wrote this already last time as some, in fact, quite precisely as the integral over orthogonal matrices, and then the integral over these diagonal matrices with ordered entries, and this was just the change of variables formula. So then you have times the Jacobian S at U lambda. Okay, so this is what we found last time. So the goal was to compute this Jacobian. And now we basically have, with these notations I reviewed, we have all the necessary tools. So let's start the computation. In fact, this argument is not a difficult one. It's really rather simple. The only problem is, well, there are two problems. One is you have to do all these restrictions to make sure that everything is nice and bijective, so that's slightly annoying. And afterwards, you just have to set up the right notations. But once it's done, the actual computations are very simple. So let's compute this. Let's first compute this this differential. So how does one do that? Well, we will apply the formula that we just saw for general Lie groups. So I take an element T in the tangent space of the orthogonal group at U, and then I take an element D in the tangent space at lambda of these ordered diagonal matrices. What is this tangent space, by the way, as a little exercise? What is this space? Yes, it's the space of diagonal matrices. It has to be a linear space. And so this is not a linear space. This is an open manifold, but this is a linear space of the diagonal matrices. So we have the following thing. So let's just apply this formula that we saw. D. So this is something, I mean, the manifold I'm working on here is the product manifold, and you know that the tangent space of a product manifold is the product of the tangent spaces and so on. And I can find this by taking precisely this formula here. Okay, so I will apply that formula, and I use the exponential map on this product manifold. So in the first component, it is T, U, well, it's U inverse, okay, well, it's U inverse, U. And then the second one is e to the T, E lambda inverse applied to lambda at T is equal to 0. Okay? So this is how I compute my differential. Now I I can just recall the definition of S. There is my function S. There's my function S. If I want, of course, I can replace this minus 1 with a star. Doesn't really matter, right? These are orthogonal matrices. So I get d over dt of this matrix, so E U. And then, so that was the first component. Then I get this diagonal matrix. And then I get the adjoint of this matrix. And then all of this is differentiated at t is equal to 0. Okay. Now let's compute this derivative. Let's compute the derivative. Now just apply the chain rule. So we have the t appears in 3 places, and then I set it to be 0 after the differentiation. So if I differentiate this guy here, then I bring down a t. What do I get? I get a t u star u. So this just gives me a t, and this is lambda u star. Okay, so this is if I differentiate here. The advantage of working with matrix Lie groups is that these are very concrete objects. These are objects that lie in a Euclidean, embedded Euclidean space. So you can just differentiate using your usual multivariable calculus. If I differentiate this guy, then I bring down a d lambda minus 1. So this gives you a d, and this gives you a u. So it's u d u star. And finally, if I differentiate that t, I get a u lambda, and then I get t star. Okay. And now I would like to make an observation about the tangent space. Does anyone know what the Lie algebra of the orthogonal group is? So these, that's not quite Hermitian matrix. It's anti-Hermitian, yes. And now everything is real. So it's real anti-Hermitian, or more commonly they're called real antisymmetric matrices. And to see that, this is a simple calculation. We will do this calculation. We will do it, in fact, at U, not just at the identity, but the calculation is the same. So how does it go? We know that this exponential map e to the t, that one, e to t star, is an orthogonal matrix, right? So this was the path that we chose on our manifold, on our Lie group. What does it mean for this to be an orthogonal matrix? It means that it times its adjoint is equal to the identity. So this is equal to the identity, and what I can do now is I can differentiate this equation in t. So if I differentiate in t, so d over dt at time t equals 0, what do I get? And I will maybe skip one step. So I get a t u star from here, and from there I get the adjoint of t u star, and they add up to 0. So t u star plus t u star star is equal to 0, which means that t u star is an antisymmetric matrix. Okay, so if U were the identity, if we were looking at the Lie algebra, this would mean that T, which is an element of the Lie algebra, would be equal to 0. Okay, so with that, I can rewrite this a bit. So I can rewrite my differential U lambda at T d as. I would like to pull out a U. I would like to write it as something U times something times U star. So these two terms are okay. In terms of the U, this one is not quite okay. So I will write a U star here. I can certainly do that. And then the U star on the right, these two are okay. This one is not. So I can put in a U star, which is just the identity. And then I notice that if I pull out the U and the U star, then here I have U star T lambda, and here I have a lambda T star U. And these two matrices, lambda T star and T lambda, are each other's adjoints. And by this, no, I don't want the T lambda, I want the T U. These two matrices. Okay, so these two matrices are each other's adjoints, right? And by what I just calculated, I find that they are in fact equal to the same matrix up to a side. So I can write all of this using a commutator. So the first term, I have a U star T, and then I have a lambda, right? That's the first term, and this is equal to minus U star T by what I just calculated. So it's the same term except you swap their order, and this gives rise to a commutator. You're taking a course on quantum mechanics, right? Does everybody know what this commutator is? Commutator of x and y is xy minus yx.
Why do you have this identity? Why T star U is equal to minus y star U?
Oh, because this is the adjoint of that matrix. So this, let me write this here. Or should I have done it the other way around? Aha, maybe I should have done it. Oh, I see what you're saying. I should probably, because I get U star T instead of T U star. Let's see. T star, yes, you're right, so it should go the other way around. So T U star. I think what let's see, did I do this right? Probably did do it right.
We need to use this identity with some, with like T, with T star instead of T and U star instead of U.
Yes, we probably need to do that, yes. So because I want to make sure, so I think this calculation was correct. So this calculation, yes, this calculation is correct. Okay, that's a good point. I will think about it. Let me come back to it after the break. I'll think about it during the break. So you are right that this calculation doesn't give you exactly what we wanted, but this nevertheless is true. So this thing is antisymmetric by a variant of this argument, which I can't quite come up with now, but I'll try to fix it later. Okay, but let's conclude the calculation. And then here we get if I pull out the U and the U star, I will get a D. Okay. I should probably start from this, right? If I want to. If I want to get, that's maybe the solution. I think I want to start from that. So certainly, if I started from this. I think this would be okay, right? I think if I started from that. Okay. So why is this matrix orthogonal? I think it's orthogonal because so T. Yes, it's orthogonal because you can do, if you take a matrix T. So T has to be in the. I think you can do a left or right translate on your Lie group. And I guess I want to write my T as U times X. Yeah, I think this does the job. So I should have, okay, so one place, so here I think I need to do a left translate instead of the right translate. X is an element of my Lie algebra. Ux is an element of my tangent space at U. Okay? And this is the exponential of something that lies in the Lie algebra, right? U star Ux lies in the Lie algebra. Okay? And therefore, this is an orthogonal matrix, and I can do this calculation. I think it's now correct, actually. Would you agree? So should I explain this a bit more carefully? So I write my. So I choose my X. X, capital X, is in the tangent space of the identity tangent space and the identity of M, and then therefore capital T, which is equal to Ux, is in the tangent space of U, and then I can define a path, a gamma of T, which is equal to. I mean, this I don't even need to define a path gamma. I just know that the exponential map e to the tx is in this thing e to the tx, which is equal to e to the t u U on the left, U star T is an orthogonal matrix. Okay? So this is an orthogonal matrix, and therefore this holds. And now I can differentiate, and now I think it comes out right. So U star T, yes, and this is equal to U T star, yes. And that's what I wanted, right? I wanted to show that U star T is equal to minus U star, minus T star U. So this, of course, I have to correct that. So this was T star. Okay. I think now it's correct, right? So thanks for pointing that out. This was not quite right. But it's so you just basically have to do, I did a right translation before when I was doing my general discussion of tangent spaces on Lie groups, and here I need a left translation. Okay. So this is what you get. So just as a reminder, this commutator is equal to x, y minus yx. And this is now a very explicit form of the differential. What I would just like to do now, so in order to facilitate the calculations, is to translate this back to the Lie algebra, so to the identity. And I will define a map, which I call A, U. In fact, it only depends on U, on lambda, sorry. A lambda, as you will see. So this is now a map on the identity, or at the tangent space, the identity. So it's the same map, except I translate everything to the identity, or if you wish, I set U to be equal to the identity. And through A lambda is equal to, so I take this map, I want to kill the U's. So how do I kill the U's? I have to multiply on the left by U star. And in the argument T, I have to multiply with the U. And then I have to multiply with a U on the right. Okay, so I chose these things, of course, in such a way that what I get in the end is the following. So it's a new map, it's a linear map where I got rid of the U's. And then there's a simple observation, is that if you stare at this definition, all of these transformations are isometries in the space, on these linear spaces of matrices. Here, what do I do to the matrix T? I apply an orthogonal rotation, which is an isometry. And here, I apply an orthogonal conjugation on the space of Hermitian matrices, which is also an isometry. So from this, one can deduce that the determinant of the map A is the same as the determinant of the map DS. So let me write this up a bit more explicitly, but there's not much more to it. It's just an observation that this map A is related to the map DS by a composition of two isometries. And therefore, their determinants are the same. These determinants, in this case, are not so easy to evaluate if you actually write down the definition of a determinant, because these all lie in somewhat high-dimensional spaces. But one can just very easily observe that these things are isometries. Okay. So then the claim is that the determinant of A lambda is equal to the determinant of ds u lambda. So let me justify this claim. So one can, I mean, if you want to be very formal, you can define this adjoint operation on the Lie group. It's usually denoted as follows. On the Lie algebra. Adjoint operation on the Lie algebra. And it's just conjugation by U. Okay. And then I define an operation which I call LU, which is just L stands for left multiplication, so it's left multiplication by U. And then, so then you can observe that A is going to be the conjugation. So what do I do? Let me start from the right, maybe. So what do I first do to my matrices TD? I apply L to T and I do nothing to D. This is the identity. And then I apply my ds u lambda. And then finally I apply this adjoint operation U. Okay. And now I just observe that LU, which is an operation from T1 from the tangent space at 1 of ON to the tangent space at U of ON, and it's an isometry. In fact, it's the canonical isometry obtained by left translation from this tangent space here to that tangent space there. And this is an isometry. And moreover, so add the operation add on the space of Hermitian matrices is also an isometry. It's just conjugation by unitary map. So that's the end of the argument. So one just has to note that this is given by composition with isometries. So these two linear maps have the same determinant. So in other words, it suffices to compute the determinant of this linear map, and that's very easy. So let me do that. There it's easiest to work with coordinates. But now we've translated everything to the identity. So it suffices. So it suffices to find the determinant of A lambda. Right? And we choose coordinates. So the range of A lambda lies in is this Hermitian or the real symmetric matrices. So let me use these coordinates A ij, whereby I is less than or equal to j. Okay, so I only talk about the upper triangular entries. The others are, of course, given. So these are the independent coordinates. What about t? So t, if you recall, t is an element here. Now t is going to be an element in here. So if I'm plugging in the argument, so A lambda is a linear map which acts on t and z. And t lies in the Lie algebra. And therefore it's an antisymmetric matrix by the computation we just saw. And antisymmetric matrices have a zero diagonal, so they are completely determined by the strict upper triangular elements. So this is my coordinates for the t, and d, of course, is my matrix D is diagonal, so that has the obvious diagonal coordinates. Okay, so then let's compute, and this is the crux of this whole computation. If I compute the element, the entry ij, I less than or equal to j, of this linear map, it is equal to, so let me recall, so what was A lambda, I erased it unfortunately, A lambda of t d was, which way around did I write it like this, t lambda of d. Okay, so how do I, let me write this in terms of the entries. So lambda is diagonal, which means I have t I j, if I is strictly less than j, and then I multiply it with a lambda j minus lambda I, and then I have a d I. So it's understood that Tij is equal to 0 if I is equal to j, and dii is equal to, let me write it like that. Okay? This is just this commutator. And now you see very explicitly what the Jacobian is, right? So here are my variables. I have a Lebesgue measure on that variable. I have a Lebesgue measure on that variable. If you want to think of it as a change of coordinates, alternatively, I mean just computing the determinant, right? So the dependence is very, very simple because there's no, the independent variables here, Tij and dii, each one of them is associated with a unique entry of Aij. There's no more mixing. So in other words, the Jacobian of this map is just going to be the product of all of these individual one-dimensional Jacobians. So here I have one-dimensional, I have one variable here, which governs the variable Aij, and then I have one variable here, dii, which governs the variable Aii. So therefore, the Jacobian, which is equal to the determinant of A lambda, as I said, the determinant of this map is just going to be the product over I strictly less than j of all of these terms, right? Here the Jacobian is 1 for each one of these guys. So it's just going to be the product I, j, lambda I minus lambda j. Okay? And that's it. This was what we wanted. We know that this is equal to the determinant of S u lambda is equal to the determinant of A So the proof, and this was this proposition 35, is complete. Okay. So the key of the proof really is this. There was a lot of preparation, some nuisance about domains and ranges. There was one non-trivial idea, which was to translate everything to the tangent space at the identity, so to the Lie algebra. That required differential geometry. Once you've done that, then the calculation on the Lie algebra is this one, and that's very easy. And you see very clearly where this Jacobian comes from in terms of the eigenvalues lambda. In particular, it does not depend on U, does not depend on the eigenvectors, and that's a remarkable fact, that the Jacobian only depends on the eigenvalues, not on the eigenvectors. Okay, so this is a good point to have a break. Let's have a break and we'll continue in 15 minutes. Okay, let me continue with one remark about GUE. So if you recall, this argument that we just did was for GOE, and exactly the same thing holds for GUE. Let me, in fact, before I give you the argument itself, I won't give the full proof. The proof is the same. But before I give the statement, let me just remind you of the map that we had. So this A, T, D. So this was the essence of the calculation, and this gave you the Jacobian. So from this we could read off the Jacobian simply by saying that there's a one-to-one relationship between off-diagonal entries of A and these Tij's, and they are just multiplied by lambda j minus lambda I. And similarly, there's a one-to-one correspondence between the diagonal entries here and the diagonal entries there. And here the coefficient is just 1. Now, if you take, so this was for GOE. If you take GUE, where is the difference? The whole argument is basically exactly the same, except at this point, you have to recall what is the Lie algebra of the group of unitary matrices. It is the set, by the same argument as before, it is the set of anti-Hermitian matrices, which means matrices with purely imaginary diagonal, and such that the upper triangular entries are given by the minus conjugate of the lower triangular entries. But in particular, the upper triangular entries can be any complex numbers you wish. So in other words, if you integrate over them, you have 2 real dimensions. You're integrating over a complex number, in other words, 2 real dimensions. So these numbers here lie in C. Which means that in the Jacobian, remember, if you have a Jacobian simply of a dilation, the dilation factor comes to the power of the dimension. And since we dilate this by the factor lambda j minus lambda I in a 2-dimensional real space, we will get the same Jacobian squared. These factors come with a square. And that's all there is to know about GUE, basically. So let me give a precise statement. So let Hn, so this is now the space of complex n by n matrices such that H is equal to H star. So this is the complex Hermitian conjugate. Then the claim is that the integral over this group is equal to some constant Cn, which I as always, don't care about. The diagonal matrices, d lambda. Now, this is now the set of unitary matrices, n by n unitary matrices, with a Haar measure U. And then I have my function, and I have my Jacobian. So now the Jacobian is the same as before, except I get the differences squared. And then I have my function f u lambda u star. Okay, so this is the statement. This is in fact more pleasant because this doesn't need an absolute value, right? It's squared, so you can write it without absolute value. And this fact is in fact important. It means that the analysis of the eigenvalue density for GUE is in fact considerably simpler than for GOE. And we will, from now on, we will focus on GUE. So the proof, let me just summarize. There's one other place if you want to make this do this very carefully. You should consider the quotient space at the beginning to make sure that you have a transformation that is bijective. You have to restrict yourself to the following set I call U plus of n, which is the group of unitary matrices quotiented by the diagonal unitary matrices. Note, by the way, this is not a group, right? This is not a normal subgroup. It's a nice manifold, but it doesn't have the group structure anymore, which is a bit annoying, but it's okay. And then D, where du of n is the set of diagonal unitary matrices. So it's unitary matrices intersected with diagonal matrices. So more precisely, it's the set of diagonal matrices where the diagonal entries lie on the unit circle, have modulus 1. Okay, and that's it. So as before, we get this. So this is, if you wish, is the final line of the proof. So as before, we have that, and this is a two-dimensional. This is a two-dimensional space, so this gives us a factor. Okay, otherwise the proof is exactly the same. Is this okay? So let me summarize what we have proved. So we have obtained a remarkable formula. It's a very famous, probably one of the most famous formulas in random matrix theory. So the joint eigenvalue distribution So the joint eigenvalue or density, let me call it the density, since they have a density with respect to Lebesgue measures, let me call it density, of, and these things can be conveniently written together. GOE and GUE can be written with using the same formula if I introduce the following classical parameter, which is called beta. So the formulas I'm about to write hold for both GUE and GOE, if you choose your beta appropriately. And then this is, so P and this is equal to, so you have some normalization factor. So these z's I never really care about, and they're just some positive numbers that ensure everything is normalized. Now, if you recall, I will not go back to that, but at the very beginning of this section, we found the density of GUE or GOE with respect to the Lebesgue measure on real symmetric or Hermitian matrices. And that had something of the density was given by e to the minus n, or n over 2 trace h squared. Right, you recall this? And this is a simple function of the eigenvalues. The trace is just a function of the eigenvalues. So we can write this e to the minus n beta over 2 as follows. So this function, so in fact the function we had was multiplied with a beta. 4 I think I need if I want. So I wanted to get, you can go back to the expressions we had, but if for the GOE we had a n over 4 trace of h squared, and for GUE we had n over 2 h squared. I think this is correct. Let me just check to make sure. Yes, so you see I can summarize them nicely like this, and then I have the Jacobian and that's to the power beta. Okay, so I can summarize both nicely. And then there's a very nice observation which people have made a lot out of in random matrix theory, is that this beta appears in both exponents, here and here. So you can write all of this as the exponential of beta times something that does not depend on beta. Let me pull out a factor n as well. So we have a sum 1/4 of all the eigenvalues. And then I have a 1 over n Okay, so you can just rewrite it like that. It's a trivial rewriting. However, this looks very appealing. If you know some statistical mechanics, if you've seen some classical statistical mechanics, this is precisely the Gibbs density of a model of n interacting classical particles. The interaction, so they are confined to an external potential, a quadratic external potential, which confines them. They interact via a logarithmic interaction potential. This is a two-body interaction, which is a funny interaction, so it's repulsive. So with this sign, you can check it's repulsive at small distances, which means particles repel. So these eigenvalues in this interpretation of statistical mechanics, they don't like to be close to each other. This is also manifest here. I mean, the density of, if two of these lambdas coincide, the density vanishes. And you see that the repulsion is stronger for GUE than for GOE. And this beta, I think, have you seen, do you know that beta? Beta in statistical mechanics is 1 over the temperature. This is the standard interpretation of beta. That's the reason people call beta this index. Now, you could also, once you see this formula, it's a rather exciting formula, you could get even more excited, and you could ask the various generalizations. You could ask, well, beta is the inverse temperature. Beta doesn't have to be 1 or 2. Beta can be any positive number. That's true. And you can analyze this probability measure for any positive beta. That's an interesting mathematical problem. There are no matrix models of this kind, at least, that correspond to other values of beta. There is a matrix model if beta is equal to 4. In fact, if you wish, this is even an exercise you can do on your own, I'm sure. If you wish, you can try to find a matrix model very similar to GUE and GOE, where beta is equal to 4. You remember how this beta arose. It arose as the dimension, the real dimension of the off-diagonal entries. So if you want beta to be 4, you need to take off-diagonal entries whose real dimension is 4, and this can be achieved by taking quaternions. So if you, instead of putting real or complex numbers in the off-diagonal entries, you put in quaternions, which is a nice associative algebra. So it leads to matrices. You can in fact view these as 2 by 2 blocks where you put in Pauli matrices. So these are very well-defined matrices. You get this, and it's called GSE for symplectic, Gaussian symplectic ensemble. And then you get the same law from a matrix model with beta is equal to 4. Beyond 1, 2, and 4, there are no matrix models of this kind that yield this measure. However, this measure, of course, can be considered as an interesting probability measure. There are different matrix models of very different nature, tri-diagonal type models, which do yield these measures, but they are quite different. So that's one thing you can ask yourself. Of course, beta can be anything. The other thing is this confining potential. So this logarithmic interaction is clearly very rigid. That's an important fact that comes from the Jacobian. You can't play with that. Could you change the quadratic interaction to be something more general? The answer is yes. You could easily, if you recall, you could easily define a probability measure on the space of Hermitian matrices just by taking you take your favorite function v, which has sufficiently fast, rapid decay at infinity, so that this measure here is indeed normalized. It's a probability measure. You can take any v. Let's say you can take a nice convex v, and then this will give you a nice probability measure on the space of real symmetric or complex Hermitian matrices, and then this v will simply appear here. So more generally, so let me then by the same argument, so by these propositions 35 and 36, this is equal to 1 over z, and then you have v and beta, and the exponential of exactly the same thing. So we have a sum I probably want 1/2. I mean, these factors 1/2 are a bit a question of convention. And then we have minus 1 over n. And this thing has a name. It's a one-dimensional okay, so this is something that is also much studied. Why one-dimensional? Well, again, the interpretation is really particles. These lambda I are particles. They live on the line, on the real line, so it's one-dimensional. Log gas, because it's a gas that interacts with a logarithmic interaction potential. And you can put in any external potential you wish, and you can also put in any temperature that you wish. And this is not it's an interesting model. It's not always very easy to analyze. Physically, it's not an extremely realistic model because this interaction, you may know this logarithmic interaction. It's a famous interaction in 2 dimensions, right? It's the Coulomb interaction in 2 dimensions, except these particles are confined to 1 dimension. So it's a very weird system. You have 2-dimensional charged particles which are confined to a line. So physically, it's not such a realistic model, but it has some nice mathematical features, and it emerges naturally from random matrices, as we just saw. Okay, so I will not study more. I will not say more about these general log gases. What I would like to do now is to start a detailed analysis of this function in a very simple case, namely GUE. So I would like to start a very detailed, obtain a very detailed understanding of this joint probability density for the simple case of GUE, which is the simplest, well, one of the simplest instances where one can study it. You will see it's already non-trivial. It's an opportunity to develop lots of powerful and rather beautiful methods. And the key word there is really orthogonal polynomials. So also determinantal point processes. We will see that the eigenvalue process that is described by this joint density is a so-called determinantal process. So from now on, so we set this inverse temperature to be equal to 2. We work with the GUE. It's convenient to rescale our eigenvalues, and in line with this analogy of particles, I will call the rescaled eigenvalues x. So xi this is just to get rid of some factors. Basically to get rid of this factor n here. So the joint law of these x's, you take the joint law of the lambdas, you plug in, you do this change of variables, and you get everything. I mean, all of the Jacobians and all of that will be absorbed into this normalization constant. So this is the joint law. So now this has become a very explicit xi. Oh yes, thank you, xi. So this has now become a very explicit problem of probability theory. So you could even ignore everything I told you about random matrices. You could just say, okay, here is a probability density on n random variables, x1 up to xn. What can I say about their distribution? In particular, so what you could ask, well, what do you mean? What can we say about their distribution? Here it is. It's very explicit. What we would like to analyze is, for example, what is the density of these x's? Well, this we in fact already know. We know it's the semicircle law. It's not at all apparent from this formula, but we have proved using different means that the density of these points is for large n given by the semicircle law. Now we would like to understand much more detailed questions, like what do the correlations of these points look like on small scales? So if I know there's a point in this region, so what is the probability of finding a point in this region and simultaneously a point in that region? And how do such things behave for large n? These are much more subtle questions. They are in general very difficult to answer. And for such a model, one can answer them. And it's related to a beautiful algebraic structure behind such expressions, and in particular behind this kind of interactions, which can be dealt with using orthogonal polynomials. So some people say that these kinds of measures have an integrable structure, and by that they mean they can be solved using explicit formulas, some non-trivial algebra. And the starting point for that is the following observation, namely that this thing this is in fact, so without the square, is the determinant of a very simple matrix. It's called the van der Monde determinant. So the claim is that for any real numbers x1 up to xn, or even complex numbers, this is equal to the determinant of the following matrix, xi to the power j minus 1. Okay? Is this clear? So this is the determinant of the following matrix. So I have x, I have 1, let's see, 1i is the index, so I have 1, and then I have x1, x2, x3, xn, and I have x1 squared, x2 squared, x3 squared, xn squared, x1 to the n, x2 to the n, x3 to the n, n minus 1, xn to the n minus 1. Okay, so it's the determinant of the following matrix. So this is just an algebraic statement about multivariable polynomials, but it's the starting point for the whole analysis we are going to do. So let me prove it. Is the statement clear? You put all of these x's into such a matrix, which is called the Vandermonde matrix. Okay, so how does the proof go? We use basic facts about polynomials. So let me call this guy p of x. So let p of x, it's a multivariable polynomial in the variables x1 up to xn. And this is the determinant xi ij goes from 1 to n. So then, now let's do some simple observations about this polynomial. Then p of degree, what's the degree of this polynomial? You can look at how is the determinant calculated. You have to take sums over all possible permutations, and then you multiply the elements along that permutation. And you will notice every permutation has precisely one entry from each column, right? So that means the combined, so the degree, by degree mean the combined degree in all of these variables. The degree is just going to be 1 plus 2 plus 3 up to plus n minus 1, right? That's going to be the degree of this matrix. So 1 plus 2 and this is n choose 2. So it's a polynomial of degree n choose 2. Moreover, p of x is equal to 0 if x is equal to xj for some I not equal to j. Okay? So that means now you can do polynomial division. You start with the first pair, x1, x2. You know that if x1 is equal to x2, p of x is equal to 0. And therefore, you can divide p of x by x1 minus x2, and you still get a polynomial. You can divide by x1 minus x3, x1 minus x4, go on. And you can divide the polynomial with this entire product here, and you will get a polynomial. So this divides, it's another polynomial which divides this polynomial P. Now what is the degree of this polynomial? It's n choose 2 again. So in other words, this polynomial divides that polynomial, and they have the same degree. That means they must be the same up to a constant. So P of x is equal to some constant times it's equal to some constant c times xj minus xi. So we're almost done. This looks good, right? We just have to show that this constant has to be equal to 1. So let's do that. So it remains to find c. And how do we do that? Well, one easy way to do that is to go back to this form here. And remember that this, as I said, so you just write down the definition of the determinant, and you get sum of all possible permutations. And let's just look at the term arising from the trivial permutation, the identity. So it's the product of the diagonal. And compare it, try to extract the same term from this product here, and compare coefficients. So we will look at term arising from the trivial permutation. And take a trivial permutation. If we take the trivial permutation here, of course, it's easy to read off. So what's the trivial permutation? So P of x is equal to 1 times x2 times x3 squared times xn to the n minus 1, right? Plus all the other permutations, but this is the diagonal one. Okay? Now, let's try to find the same term. And these are polynomials, so it's enough to compare coefficients, right? So let's just find the same term in this polynomial here. So same term in this. So c times product I less than j, xj minus xi. So let's look, what do we need to find? So we need to find xn to the n minus 1. What does that mean? Xn, so j, so the j has to be n, and then I take, so maybe, I mean, you can, I don't want to write this out fully, but let me explain it in words. It's kind of obvious, you can see it. I take j is equal to n, and then I take I going all the way from 1 to n minus 1, and from each one of these factors I have to pick this guy. I multiply out the whole big product. I have to always take this guy. If I once do not take this one, I will get a too low exponent here. So I always take all the factors, from all the factors when j is equal to n, I take the first one here. Okay. Then I consider all the factors when j is equal to n minus 1, and here I have to, again, I always have to take the first one. Because I have n minus 2 terms, and I have to take them all, from each one of them I have to take the x n minus 1. And so on. So I always have to pick this guy. It amounts to always picking the first term from this product. And then, of course, I get many other terms, but they are the other ones. And here we are. And now we saw that this multiplies the c, and therefore the c has to be equal to 1. Okay, is all right. So this is this van der Monde determinant, which is a, as I said, a powerful observation, and the reason behind its power is the following simple, trivial consequence, which uses the fact that if you take a determinant, if you take a determinant and you add a linear, determinants do not change if you add a linear combination of any of the other rows to one row. So basically it's saying that when instead of taking, if I replace this xi to the j minus 1, if I replace it with any other polynomial of degree j minus 1, such that it's the coefficient in front of x to the j minus 1 is still 1, I get the same thing. So this determinant does not change if I add lower order terms, let's say an xi to the j minus 2, this will not change the determinant. I just have to make sure that the coefficient in front of the top degree term remains 1, and such polynomials are called monic. You may have encountered this terminology. So this is monic. So if its highest coefficient is 1. And then we have a proposition monic polynomial of degree I. Maybe I should, well, maybe it's okay. Then, so the claim is I can replace this monomial x to the j minus 1 with a polynomial p j minus 1, any polynomial. So the proof, there's nothing to say about the proof, it's immediate, right? Just by using the fact from, I mean, if you want to, you can try to write down a very formal proof by induction maybe, but there's, you see, it's just saying that if you start, we know that this guy is equal to x I to the j minus 1. And it's just saying that if I can take any linear combination, for example, look at the row, let's say look at the column, the last column, where I have the powers n minus 1. I can take any linear combination of the preceding n minus 1 columns and add it to that last column. I will not change the determinant, right? This is a deep fact about determinants. And in particular, using these linear combinations, I can make this monomial any monic polynomial. I can't touch the top coefficient. I can't touch the j minus 1 coefficient, the coefficients in front of xi to the j minus 1. I can modify all the others as I wish, using operations which leave the determinant invariant. So the proof. So we are using, I mean, this in principle is something you could check, right? You could pick your favorite monic polynomial and compute this determinant, but it's not easy. It's not easy in general to check that such an identity holds. Right? So, but using these invariance properties of determinants, we find it immediately. And this is tremendously useful, you see, because it gives us a huge amount of freedom in choosing these polynomials. So in the van der Monde determinant, we chose the polynomials to be the specific monomials. But for the computation that we want to do, this is no good at all. We would like to choose completely different polynomials, a certain family of polynomials which are orthogonal with respect to some measure. And that we can do, because we can choose any polynomial we wish, thanks to this proposition 39. Okay, is this clear so far? All right. So how does it? Maybe now is a good point to stop, since what I would like to do now is to start developing the argument how to find these polynomials. So let's stop here, and next time we will figure out how to choose these polynomials in such a way that we can perform all of the integrations that we would like to do. Okay, so we'll stop here.